far beyond our galaxy, far beyond the quiet stars of the Milky Way, in a distant region of the universe, something extraordinary is happening. A cosmic collision, not between planets, not between stars, but between black holes. In the heart of a distant galaxy, two black holes orbit one another in a violent gravitational dance. One of them is unimaginably massive, billions of times heavier than the Sun. The other, smaller yet still monstrous, circling its giant companion again and again. Every few years, the smaller black hole plunges through the enormous disk of glowing gas surrounding the larger one. When it does, the universe flashes, a burst of light so powerful it can be seen across billions of light years. Astronomers have watched these flashes for more than a century. Regular, predictable, like cosmic clockwork. The system responsible for these explosions has a simple name: OJ-287, a distant galaxy, nearly 5 billion light-years away. But inside it, two black holes are locked in one of the most extreme gravitational interactions ever observed. A system where gravity bends space, time slows down, and Einstein's theories are tested on a cosmic scale. Tonight, we explore one of the most mysterious objects ever discovered, a place where two black holes orbit each other, and the universe itself trembles with every encounter. This is OJ-287. The universe is filled with distant lights, stars scattered across the darkness, galaxies glowing faintly billions of light years away. Most of these lights remain constant, steady, predictable, unchanging. But sometimes, astronomers notice something unusual, a star that suddenly brightens, a galaxy that flickers, a distant object that flashes with enormous energy and then slowly fades. These changes are not random. They are signals, clues that something powerful is happening somewhere in the cosmos. One such signal was first noticed more than a century ago. At the end of the 19th century, astronomers began carefully photographing the night sky. Using long exposure plates, they captured faint objects invisible to the human eye. These photographic plates allowed scientists to compare images of the sky taken years apart, and sometimes they noticed something strange. One object in particular seemed to behave differently. It appeared faint in some photographs, but in others, it suddenly became much brighter. Then it faded again. Years later, it brightened once more. At first, astronomers assumed this was just another variable object, perhaps a distant star that occasionally flared, or a galaxy with an active center. But as more observations accumulated, a pattern began to emerge. The brightening events were not random. They followed a schedule. Roughly every 12 years, the object would suddenly become dramatically brighter, then slowly fade again. This strange repeating signal puzzled astronomers for decades. The object itself was located incredibly far away, nearly 5 billion light-years from Earth, a distance so vast that the light reaching us today began its journey long before life appeared on Earth. This object became known as OJ-287. At first, it appeared to be just another distant galaxy, but the repeated flashes suggested something far more dramatic was happening inside it. Throughout the 20th century, astronomers continued to monitor OJ-287. Each time the predicted year approached, Telescopes around the world watched carefully, and almost every time, the burst arrived exactly as expected. A sudden surge of light, then a slow fading, then darkness again. These repeating outbursts became one of the most intriguing mysteries in astronomy. What could possibly create such enormous flashes on such a regular schedule? The answer would take decades to uncover, but it would eventually reveal something extraordinary. Because the center of OJ287 is not home to one black hole, it contains two, a binary system of black holes locked together in a gravitational dance. But to understand this discovery, we must first understand what lies at the heart of most galaxies. At the center of our own galaxy, the Milky Way, lies a black hole, a supermassive black hole known as Sagittarius A star. Its mass is about 4 million times greater than the Sun. That may sound enormous, but in cosmic terms, it is relatively modest. Some galaxies contain black holes far larger, billions of times more massive than our Sun. These giants sit quietly in the centers of galaxies, surrounded by enormous disks of gas and dust. Material spirals inward toward the black hole, heating up as it falls. Friction and gravity compress the gas until it becomes incredibly hot, millions of degrees. At those temperatures, the material begins to glow. Bright streams of energy shoot outward from the galactic core. These glowing regions are called active galactic nuclei, and they can shine brighter than entire galaxies. OJ287 is one of these active galaxies. At its center lies a supermassive black hole of almost unimaginable size. Scientists estimate its mass at nearly 18 billion times the mass of the Sun. To put that into perspective, if this black hole replaced the Sun at the center of our solar system, its event horizon would extend far beyond the orbit of Pluto, an object so massive that its gravity bends space itself. But this giant is not alone. Orbiting around it is another black hole, smaller but still enormous. This secondary black hole has a mass of roughly 150 million suns, and it follows an elongated orbit around the central giant. The orbit takes about 12 years to complete. Every 12 years, the smaller black hole swings close to the larger one, but its path does something remarkable. Instead of simply orbiting outside the surrounding gas disk, the smaller black hole plunges directly through it. The central giant is surrounded by an enormous disk of glowing gas. This disk forms as matter spirals toward the black hole. The material rotates faster and faster as it falls inward, heating to incredible temperatures. When the smaller black hole crosses this disk, it crashes through the gas at tremendous speed. The impact releases an enormous amount of energy. Gas is violently heated and ejected outward. The collision creates a brilliant flash of light, a flare so powerful it can be detected across billions of light years. And this is the flash astronomers observe from Earth. But the event does not happen just once, because the smaller black hole crosses the disk twice during each orbit. Once as it moves inward toward the central black hole, and once again as it moves outward. Each crossing creates a burst of energy, two flashes separated by a predictable amount of time. This pattern explains the mysterious signals astronomers observed for more than a century. OJ287 is not a random flickering galaxy. It is a binary black hole system, a pair of black holes orbiting each other in one of the most extreme gravitational environments ever observed. Yet even this explanation does not capture the full complexity of the system. Because the orbit of the smaller black hole is not stable, the immense gravity of the larger black hole distorts space itself. According to Einstein's theory of general relativity, mass bends space-time. And when objects move through that curved space-time, their orbits shift. The path of the smaller black hole slowly changes with each orbit. The orbit precesses, rotating slightly over time. This means the timing of the disk crossings changes very slightly every cycle. Yet astronomers have been able to predict these changes with astonishing accuracy. By applying Einstein's equations to the system, scientists can calculate exactly when the next flare should appear, and again, the predictions have proven correct. OJ-287 has become one of the most important laboratories for testing general relativity on cosmic scales, a system where gravity is so extreme that the fabric of space-time itself becomes part of the story. But this violent dance between two black holes raises another question. How did such a system form? Because black holes do not usually exist in pairs like this. To answer that question, we must travel back billions of years, back to a time when galaxies themselves were colliding, when enormous structures merged together, and when the black holes at their centers were drawn into an inevitable gravitational encounter. An encounter that would eventually create one of the most extraordinary systems ever discovered in the universe. The universe is not still. At first glance, the night sky appears calm. Stars seem fixed in place. Galaxies appear distant and quiet. But on the largest scales, the universe is constantly changing. Galaxies move, slowly, almost imperceptibly. They drift through space, pulled by gravity, drawn toward one another over billions of years. And when galaxies meet, they do not simply pass by. They collide. These collisions are among the most dramatic events in the universe. Yet they happen in slow motion. Because galaxies are enormous, the distance between their stars is vast. When two galaxies approach each other, the first contact may take hundreds of millions of years. Gravity begins to distort their shapes. Spiral arms stretch and twist. Streams of stars are pulled outward into long glowing tails. Gas clouds crash together, triggering massive waves of star formation. Entire regions of space ignite with newborn stars. Eventually, the two galaxies begin to merge. Their stars mix together, forming a single, larger system. But something else happens during this process, something hidden in the very centers of the galaxies. Because most galaxies contain supermassive black holes at their cores. These black holes are millions or billions of times heavier than the Sun. And when galaxies merge, their black holes do not disappear. Instead, they are pulled together by gravity. At first, the two black holes orbit far apart, separated by thousands of light years. But slowly, gravitational interactions with surrounding stars and gas bring them closer. Over millions of years, their orbit shrinks. The black holes spiral inward. Eventually, they form a binary system. Two enormous black holes orbiting each other in the heart of a newly merged galaxy. This is likely how OJ-287 was born. Long ago, billions of years in the past, two galaxies collided. Their stars mixed together, their gas clouds merged, and at the center of the new galaxy, two supermassive black holes began their slow gravitational dance. At first, the black holes would have been extremely far apart, but gravity never rests. Each time a star passed near the pair, energy was transferred. The star might be flung outward into intergalactic space, and the black holes would move slightly closer together. Gas clouds could also influence the process. Materials spiraling into the black holes created enormous disks of glowing plasma. These disks acted like cosmic brakes. As the black holes moved through the gas, they lost energy. Their orbit tightened, closer and closer and closer. Eventually, the two black holes reached the configuration we observe today. A giant black hole, nearly 18 billion times the mass of the Sun, and a smaller companion, about 150 million solar masses, still enormous by any standard, but tiny compared to the central giant. The smaller black hole now follows a highly elongated orbit. Instead of circling the giant in a smooth path, it travels in a stretched ellipse, sometimes far away, sometimes plunging deep into the gravitational well of the larger black hole. During these close encounters, the environment becomes extremely violent. The central black hole is surrounded by a vast accretion disk, a rotating disk of gas and dust spiraling toward the event horizon. This disk glows with extraordinary brightness. Temperatures within the disk can reach millions of degrees. Magnetic fields twist and snap. Jets of energy may shoot outward from the poles of the black hole, extending thousands of light years into space. When the smaller black hole approaches this region, its orbit carries it directly through the disk. Imagine an object moving at enormous speed, plunging through a blazing sea of plasma. The result is explosive. Gas is violently displaced. Shock waves ripple through the disk. Energy is released in a powerful flash of light. From Earth, this appears as one of the bright flares of OJ-287. But the story does not end there, because the smaller black hole continues its orbit. It eventually emerges from the disk, moving outward again. Months later, it crosses the disk a second time, and another burst of energy appears. Two flashes during each orbit, two signals repeating every 12 years. But the gravitational interaction between the black holes does something even more remarkable. It alters the orbit itself. In ordinary gravity, an orbit remains stable. Planets circle their stars in predictable paths. But near a supermassive black hole, gravity behaves differently. The enormous mass of the central black hole warps spacetime itself. According to Einstein's theory of general relativity, massive objects bend the geometry of space and time. Objects moving through this curved spacetime do not follow perfectly closed orbits. Instead, their paths slowly rotate. This effect is known as orbital precession. It was first observed in the orbit of Mercury around the Sun. But near a supermassive black hole, the effect becomes dramatically stronger. In the OJ-287 system, the orbit of the smaller black hole rotates significantly with each cycle. After every orbit, the point of closest approach shifts. The path of the smaller black hole slowly spirals around the giant. This shifting orbit changes the timing of the disk crossings. Yet astronomers have been able to predict these changes with incredible precision. Using the equations of general relativity, scientists calculate exactly when the smaller black hole should strike the disk, and again, the flares appear right on schedule. This makes OJ 2871 one of the most important natural laboratories for studying gravity. It allows astronomers to test Einstein's theory under conditions far more extreme than anything in our solar system. But the system holds another secret. Because the two black holes are not simply orbiting each other, they are also slowly moving closer together. Each orbit releases tiny ripples in space-time. These ripples are known as gravitational waves. Predicted by Einstein in 1916, gravitational waves are disturbances that travel through space-time itself. When massive objects accelerate, they generate these waves, but only the most extreme events produce waves strong enough to be detected. The collision of black holes, the explosion of massive stars, or the merging of neutron stars. In the case of OJ 287, the orbiting black holes emit gravitational waves continuously. Each orbit drains a tiny amount of energy from the system. The orbit shrinks, slowly tightening over time. One day, far in the future, the two black holes may finally merge. When that happens, the collision will release an enormous burst of gravitational energy, a wave that could ripple across the universe. But that moment lies millions of years ahead. For now, the two black holes remain locked in their cosmic dance, a giant and its companion, circling each other in one of the most extreme environments ever discovered. And every 12 years, when the smaller black hole crashes through the blazing disk of gas, the universe lights up. A signal from deep space, a flash of energy traveling across billions of light years, reminding us that even the darkest objects in the universe can produce extraordinary light. At the heart of the OJ 287 system, there is a monster, not a star, not a galaxy, but something far more extreme. A supermassive black hole so enormous that it defies imagination. Its mass is estimated at nearly 18 billion times the mass of the Sun. To understand the scale of that number, we need perspective. Our Sun already contains 99.8% of all the mass in the solar system. Every planet, every moon, every asteroid combined barely compares to the Sun. Now imagine something 18 billion times heavier, an object so massive that its gravitational pull dominates an entire galaxy. If this black hole were placed at the center of our solar system, its event horizon, the boundary beyond which nothing can escape, would stretch far beyond the orbit of Pluto. Light itself could not escape its grip. This immense object sits at the center of the galaxy that contains OJ 287. But it does not simply sit quietly. Like many supermassive black holes, it feeds. Surrounding the black hole is an enormous disk of gas and dust. This structure is known as an accretion disk. Matter in the galaxy slowly drifts toward the center. Gas clouds collapse inward under gravity. Stars may wander too close. Everything that approaches the black hole begins to spiral inward, but the material does not fall directly into the event horizon. Instead, it forms a rotating disk. As gas circles the black hole, friction between particles heats the material to extraordinary temperatures, millions of degrees. At those temperatures, the gas glows. brilliant streams of radiation are produced. The region around the black hole becomes one of the brightest places in the universe. This glowing disk is what astronomers observe from Earth. Even though the galaxy containing OJ 287 is billions of light years away, the energy produced near the black hole is powerful enough to be detected across cosmic distances. But the disk is not a calm structure. It is violent, turbulent. Magnetic fields twist through the plasma. Particles accelerate to near the speed of light. Occasionally, enormous jets of energy erupt from the poles of the black hole. These jets shoot outward into space for thousands of light years. Traveling at nearly the speed of light, they carry enormous amounts of energy away from the system. Such jets are among the most powerful phenomena in the universe. They are capable of influencing entire galaxies, heating gas clouds, disrupting star formation, and shaping the environment of intergalactic space. But in the case of OJ 287, the disk surrounding the black hole has an additional role, because it is this disk that the smaller black hole crashes through during its orbit. Imagine the scale of this event. A black hole 150 million times the mass of the Sun moving at incredible speed, plunging through a blazing disk of superheated gas. The collision releases a tremendous burst of energy. Gas is violently pushed aside. Shock waves ripple through the disk. Matter is thrown outward in enormous arcs. The impact heats the surrounding gas to even higher temperatures. And the result is light, a sudden flare bright enough to be seen across billions of light years. But the central black hole's enormous mass does more than power these events. It also distorts the very fabric of spacetime. According to Einstein's theory of general relativity, mass and gravity are not separate forces. Mass actually bends spacetime itself. Objects move along the curves created by this distortion. Near a supermassive black hole, the curvature becomes extreme. Space and time behave in strange ways. If you could somehow approach the event horizon of such a black hole, time itself would begin to slow. To a distant observer, clocks near the black hole would appear to tick more slowly. Light leaving the region would lose energy, shifting toward longer wavelengths. This effect is known as gravitational redshift, but even stranger effects occur closer to the event horizon. The gravitational field becomes so strong that space itself begins to stretch. Objects approaching the black hole would experience enormous tidal forces. These forces would stretch matter into long, thin streams, a process sometimes called spaghettification. Stars that wander too close to a supermassive black hole can be torn apart in this way, their material stretched into glowing streams of gas, feeding the accretion disk. In the OJ 287 system, the smaller black hole avoids this fate. Despite the enormous gravity of the central giant, its orbit remains stable. But the effects of relativity are still visible. The orbit of the smaller black hole does not remain fixed. Instead, it rotates over time. Each orbit shifts slightly. The path slowly turns, tracing a spiraling pattern around the central giant. This relativistic precession is far stronger than anything seen in our solar system. It provides astronomers with an extraordinary opportunity. By measuring the timing of the flares produced when the smaller black hole crosses the disk, scientists can test Einstein's equations with remarkable precision. If the theory of general relativity were incorrect, even slightly, the predicted timing of the flares would be wrong. But again and again, the predictions match the observations. OJ-287 has become one of the best natural laboratories for studying gravity under extreme conditions. A place where Einstein's theory continues to pass some of its most difficult tests. Yet the system still contains mysteries. One of the biggest questions involves the spin of the central black hole. Black holes are not just massive, they can also rotate. In fact, many supermassive black holes spin incredibly fast. This rotation drags spacetime around with it, a phenomenon known as frame dragging. If the black hole in OJ-287 rotates rapidly, it could influence the orbit of the smaller black hole, twisting the path slightly, altering the timing of the disk crossings. By carefully measuring the flare events, astronomers can estimate how fast the giant black hole spins. This allows scientists to study the physics of black holes in ways that would otherwise be impossible. But the most dramatic moment in the life of this system still lies in the distant future, because the two black holes are slowly spiraling toward each other. Each orbit releases gravitational waves, tiny ripples in space-time that carry energy away from the system. Over millions of years, this energy loss causes the orbit to shrink, closer and closer. Eventually, the two black holes will merge. When that happens, the collision will release an enormous burst of gravitational waves, a signal powerful enough to ripple across the universe. But that moment is still far away. For now, the giant black hole at the center of OJ-287 continues to dominate its environment. A gravitational titan surrounded by blazing gas, a cosmic engine producing energy on unimaginable scales. And every 12 years, when its smaller companion plunges through the glowing disk, the universe witnesses another flash of light, a signal from one of the most extreme systems ever discovered in deep space. For more than a century, OJ-287 has been flashing, not randomly, not chaotically, but with a strange, almost clock-like rhythm. Roughly every 12 years, astronomers observe a powerful outburst of light from this distant galaxy. The brightness suddenly increases, then slowly fades, and after many years of quiet, the flare appears again. At first, the pattern seemed mysterious. The universe is filled with violent phenomena. Stars explode, black holes consume gas, galaxies collide. But most of these events are unpredictable. They occur once and never repeat in the same way. OJ-287 was different. Its outbursts followed a pattern, and not just any pattern, a precise gravitational schedule. The explanation lies in the extraordinary motion of the smaller black hole orbiting the giant. The orbit of this black hole is not circular. It is stretched into a long ellipse. For most of its orbit, the smaller black hole travels far from the central giant. The gravitational pull weakens slightly. The environment becomes calmer, but eventually, the orbit carries the smaller black hole back toward the center, closer and closer, until it approaches the glowing disk of gas surrounding the massive black hole. This disk is enormous, a swirling structure of plasma and dust that stretches across vast distances. It glows with intense radiation as material spirals inward toward the event horizon. Temperatures inside the disk can reach millions of degrees. Particles collide constantly. Magnetic fields twist and snap. It is one of the most energetic environments in the universe. When the smaller black hole arrives at this region, it does not simply pass nearby. Its orbit plunges directly through the disk. The speed of the smaller black hole at this moment is extraordinary. It moves through space at tens of thousands of kilometers per second. When it strikes the disk, the collision releases enormous energy. Imagine an object heavier than 150 million suns smashing through a sea of blazing plasma. Gas is violently displaced. Shockwaves ripple outward through the disk. Material is heated to even higher temperatures. A huge bubble of hot gas expands outward from the impact point, and the system suddenly becomes brighter. From Earth, billions of light years away, astronomers see this as a flare, a sudden increase in brightness from the distant galaxy. But the event does not happen only once during the orbit, because the smaller black hole crosses the disk twice. First, as it moves inward toward the giant black hole, then again, months later, as it moves outward. Each crossing produces a burst of light, two flashes, separated in time, both tied to the same orbital cycle. For decades, astronomers struggled to explain these repeating flares. But in the late 20th century, scientists developed a model that finally made sense of the observations. OJ-287 is not powered by a single black hole. It is a binary black hole system. Two enormous gravitational objects orbiting each other. One extremely massive, the other smaller, yet still enormous. This model explained the repeating flares, but it also revealed something even more remarkable, because the orbit of the smaller black hole is not stable. Each time it circles the giant, its path changes slightly. This change occurs because of the extreme curvature of spacetime around the massive black hole. According to Einstein's theory of general relativity, mass bends the fabric of spacetime. Objects moving through this curved geometry follow paths that gradually rotate. This effect is called relativistic precession. It was first detected in the orbit of Mercury around the Sun. But near a supermassive black hole, the effect becomes far stronger. In the OJ-287 system, the orbit of the smaller black hole rotates significantly during each cycle. The point of closest approach slowly shifts. This means the timing of the disk crossings changes slightly over time. Yet astronomers can calculate these shifts with astonishing precision. Using Einstein's equations, scientists predict exactly when the next flare should occur, and again, the predictions have proven correct. For example, astronomers successfully predicted major flares in 1994, 2005, 2007, and 2015. Each time, telescopes around the world were ready, and each time, the flare appeared almost exactly on schedule. This remarkable accuracy has turned OJ-287 into one of the most important laboratories for testing general relativity, because the system allows scientists to observe gravity under conditions far more extreme than anything found in our solar system. The black holes in OJ-287 move through spacetime that is deeply warped by their enormous mass. Their motion generates gravitational effects that can be measured across billions of light years. But the system also reveals something else, something predicted by Einstein more than a century ago: gravitational waves. When massive objects accelerate, they produce ripples in spacetime. These ripples travel outward at the speed of light, carrying energy away from the system. In the OJ287 binary, the two black holes orbit each other continuously. As they move, they generate gravitational waves. The energy carried away by these waves slowly changes the orbit. Over time, the black holes move slightly closer together. The orbit shrinks, and the cycle gradually speeds up. The process is incredibly slow. It may take millions of years before the two black holes finally merge, but the gradual change can already be detected. By studying the timing of the flares, astronomers can measure how the orbit evolves over time. This provides a unique opportunity to study gravitational waves long before the final collision occurs. Eventually, far in the future, the orbit will shrink enough that the two black holes collide. When that happens, the merger will release an enormous burst of gravitational energy, a wave powerful enough to ripple across the universe. But for now, the system remains in its long repeating cycle. The smaller black hole continues its orbit, 12 years, again and again. Each time it approaches the disk, the universe prepares for another flash, a burst of light traveling across billions of light years, a signal that began its journey long before the dinosaurs walked the Earth. And that arrives here, in our telescopes, as a brief flicker from the depths of space. A reminder that even in the darkest regions of the cosmos, two black holes are locked in a cosmic dance. For centuries, gravity seemed simple. Objects fall toward each other. Planets orbit their stars. Moons circle planets. From everyday experience, gravity appeared predictable. Isaac Newton described it with remarkable accuracy. His equations explain the motion of planets, the fall of an apple, and the paths of comets across the sky. For more than 200 years, Newton's theory worked perfectly. But as scientists began studying the universe more carefully, small mysteries appeared. One of them involved the orbit of Mercury. Mercury does not move in a perfect ellipse around the Sun. Its orbit slowly rotates over time, a tiny shift, but measurable. Newton's equations could explain most of the motion, but a small part remained unexplained. It would take a new theory to understand it. In 1915, Albert Einstein introduced a revolutionary idea. Gravity was not simply a force pulling objects together. Instead, gravity was the result of curved spacetime. Mass bends the fabric of space and time itself. Objects moving through this curved geometry follow paths shaped by that curvature. This new theory became known as general relativity, and it changed how scientists understood the universe. Near massive objects, space-time becomes strongly curved, light bends, time slows, and orbits behave in ways Newton's theory cannot predict. Mercury's strange orbit, it turned out, was the first confirmation of Einstein's idea. But the solar system offers only mild examples of relativistic effects. The Sun is massive, but not extreme. To truly test Einstein's theory, scientists needed environments where gravity becomes much stronger, places where space-time is severely distorted, and few places in the universe are more extreme than binary black hole systems, especially one like OJ 287. Here, gravity reaches levels almost impossible to imagine. The central black hole alone weighs 18 billion times more than the Sun. Its gravitational field bends space-time dramatically. Anything moving near it experiences powerful relativistic effects, and the smaller black hole orbiting this giant provides the perfect probe. Each orbit carries it deep into the warped space-time around the massive black hole. Its path reveals how gravity behaves under these extreme conditions. The most obvious effect is the precession of its orbit. In Newtonian gravity, an orbit repeats exactly. Each cycle follows the same path. But in curved space-time, the path shifts. The orbit slowly rotates. Each time the smaller black hole circles the giant, the closest point of its orbit moves slightly. This shift is called relativistic precession. In the OJ 287 system, the precession is enormous, far greater than the tiny shift observed in Mercury's orbit. The path of the smaller black hole rotates significantly with every cycle. This means the exact timing of the disk crossings changes over time. But Einstein's equations allow scientists to calculate these changes. By modeling the system using general relativity, astronomers can predict exactly when the next flare should occur. If the theory were wrong, the predicted flare would appear at the wrong time. Yet again and again, the predictions have been correct. One of the most dramatic confirmations came in 2015. Astronomers predicted a major flare from OJ 287. Telescopes around the world prepared to observe the event, and almost exactly on schedule, the galaxy brightened. A flash of light traveling across 5 billion light-years reached Earth exactly when Einstein's equations predicted. This remarkable agreement strengthened confidence in general relativity. But OJ 287 provides more than just a test of orbital motion. It also allows scientists to study another relativistic effect: the spin of the black hole. Black holes are not only massive, they can also rotate. When a black hole spins, it drags space-time around with it. This effect is known as frame dragging. Imagine space-time as a fabric. A rotating black hole twists that fabric as it spins. Objects moving nearby feel this twisting motion. Their orbits shift slightly in response. In the OJ 287 system, the enormous central black hole likely rotates rapidly. This rotation affects the orbit of the smaller black hole. By studying the exact timing of the flares, astronomers can estimate how fast the giant black hole spins. This is extremely valuable information because measuring the spin of distant black holes is usually very difficult. Yet OJ 287 provides a natural method for doing so. Another effect predicted by general relativity also appears in this system: gravitational waves. When massive objects accelerate, they disturb space-time itself. These disturbances travel outward as ripples in space-time, just as waves travel across the surface of water. Einstein predicted these waves in 1916. But for decades, no one had the technology to detect them. That changed in 2015, when the LIGO Observatory detected gravitational waves produced by merging black holes. These detections opened a new way of studying the universe. Instead of observing light, scientists could now observe the vibrations of space-time itself. But OJ287 produces gravitational waves in a different way. The black holes in this system are still orbiting. They have not yet merged, yet their motion continuously generates gravitational waves. Each orbit releases a tiny amount of energy into spacetime. Over time, this energy loss slowly shrinks the orbit. The black holes move closer together. The process is incredibly slow, but measurable. By tracking the timing of the flares over many decades, astronomers can observe how the orbit evolves. This allows them to study gravitational waves long before the final collision occurs. Eventually, millions of years from now, the orbit will shrink enough that the two black holes merge. When that happens, the energy released will be enormous. The collision will produce one of the most powerful gravitational wave signals in the universe. But long before that dramatic moment, OJ287 continues to serve another purpose. It acts as a cosmic laboratory, a place where the laws of physics can be tested under extreme conditions. The system allows scientists to explore how gravity behaves near supermassive black holes, how spacetime bends under immense mass, how energy moves through curved geometry, and how the predictions of Einstein's theory hold up in one of the most violent environments known. More than a century after Einstein proposed general relativity, the theory continues to pass every test, from the orbit of Mercury to the collision of black holes to the strange repeating flares of OJ287. Each observation strengthens our understanding of gravity, yet the system still holds mysteries. Questions remain about the exact structure of the accretion disk, about the spin of the giant black hole, about how the orbit will evolve in the distant future. But one thing is clear. In a galaxy billions of light years away, two black holes are dancing, and in that dance, the universe reveals the deepest laws of space and time. In the vast silence of space, there are waves, not waves of water, not waves of light, but waves in the fabric of the universe itself. For most of human history, space-time seemed completely still, invisible, untouchable. But according to Einstein's theory of general relativity, space-time is not rigid. It behaves more like a flexible fabric. Mass bends it, motion disturbs it, and when extremely massive objects move through it, space-time can ripple. These ripples are called gravitational waves. Einstein predicted their existence in 1916, but for decades, they remained only an idea. The waves were expected to be incredibly weak. Even the most violent cosmic events would produce distortions smaller than the width of a proton by the time they reached Earth. Detecting them seemed nearly impossible, yet the universe continued producing them. Whenever massive objects accelerate, gravitational waves are born, two stars orbiting each other, two neutron stars spiraling inward, or two black holes moving through space. In these moments, space-time trembles, and the waves spread outward across the cosmos at the speed of light. For a century, scientists searched for proof that these waves existed. Then, in 2015, the first direct detection finally arrived. The LIGO observatory recorded gravitational waves produced by two merging black holes more than 1 billion light-years away. The signal lasted only a fraction of a second, but it confirmed one of the most important predictions in modern physics. and it opened a completely new way to study the universe. Instead of observing light, scientists could now observe spacetime itself. But gravitational waves do not only appear during catastrophic collisions. They are also produced by systems that orbit each other: binary stars, binary neutron stars, and binary black holes. Each orbit sends tiny ripples through spacetime. Usually, these ripples are far too small to detect, but the system known as OJ287 is different because the objects involved are so massive. One black hole in this system weighs nearly 18 billion times the mass of the Sun. The other, though smaller, still contains 150 million solar masses. When objects this heavy move through space-time, the effects are enormous. Every orbit releases gravitational waves. Each wave carries a small amount of energy away from the system, and that energy loss slowly changes the orbit. The two black holes begin to spiral inward, closer and closer. This process is incredibly slow. The system may take millions of years before the final collision occurs. But even now, the orbit is gradually shrinking, and this slow change can be measured. The timing of the flares in OJ287 provides the key. Remember, each flare occurs when the smaller black hole plunges through the accretion disk surrounding the giant. If the orbit were perfectly stable, the flares would occur at exactly the same intervals forever, but they do not. Instead, the timing shifts slightly. The flares arrive a little earlier than expected. This shift reveals something important. The orbit is slowly tightening. Energy is leaving the system, and that energy is being carried away by gravitational waves. By carefully studying these changes, astronomers can measure how much energy the system is losing. The results match the predictions of general relativity with remarkable accuracy. Another confirmation of Einstein's theory. But OJ287 offers something else, something that makes it especially valuable to scientists studying gravitational waves. Because the black holes in this system are extremely massive, the gravitational waves they produce are very long in wavelength, much longer than the waves detected by instruments like LIGO. Current detectors are designed to observe high-frequency waves from relatively small black holes. But systems like OJ287 produce waves with much lower frequencies. Detecting those waves requires different technology. In the future, new observatories may be able to detect these signals. One planned mission is the Laser Interferometer Space Antenna, or LISA. Instead of operating on Earth, LISA will be placed in space. 3 spacecraft will form a gigantic triangle millions of kilometers across. By measuring tiny changes in the distance between the spacecraft, LISA will detect gravitational waves passing through the solar system. And systems like OJ287 are exactly the kind of sources scientists hope to observe. The gravitational waves produced by this binary black hole system may one day be detected directly. When that happens, astronomers will gain an entirely new view of the system. Light reveals the flares from the accretion disk, but gravitational waves reveal the motion of the black holes themselves. Together, these observations would provide an unprecedented understanding of how supermassive black holes interact. But even without direct detection, OJ287 already tells us something remarkable. It shows that gravitational waves are not rare. They are constantly moving through the universe. Every binary system produces them. Every orbit sends ripples through spacetime. Most are too small to detect, but collectively, they fill the universe with a background hum of gravitational energy, a faint cosmic vibration, invisible, yet everywhere. And in rare systems like OJ287, the waves become strong enough to leave measurable fingerprints. The slow tightening of the orbit, the shifting schedule of the flares, the gradual spiral of the smaller black hole toward the giant. All of these are signs of energy escaping the system through space-time itself. In the distant future, this process will reach its climax. As the orbit shrinks, the black holes will move faster and faster. The gravitational waves will grow stronger. The two giants will spiral closer together until finally they collide. When that moment arrives, the universe will shake. A massive burst of gravitational waves will spread outward in every direction. Space-time itself will ring like a bell. And somewhere, perhaps billions of years in the future, distant civilizations may detect that signal, a ripple that began in a galaxy billions of light years away. But that moment is still far ahead. For now, the system continues its long and patient dance. Two black holes orbiting in darkness, sending silent waves through space-time, ripples that travel across the universe, carrying the story of their motion through the fabric of reality itself. Around the central giant of OJ287, there is a sea of light, not a solid surface, not a calm atmosphere, but a vast, glowing structure made of gas and plasma. This is the accretion disk, a rotating disk of matter slowly spiraling toward the black hole. At first glance, it might sound simple. Gas falls toward the black hole. It forms a disk and eventually disappears beyond the event horizon. But the reality is far more violent, because nothing near a supermassive black hole behaves quietly. The material that forms the disk begins its journey far from the center of the galaxy. Gas clouds drift through interstellar space. Dust gathers between stars. Sometimes entire stars wander too close to the gravitational pull of the black hole. As gravity takes hold, the material begins to fall inward, but it does not plunge directly toward the center. Instead, the gas begins to spin, just like water circling a drain. Angular momentum forces the gas to spread into a rotating disk. The farther material lies from the black hole, the slower it moves. But closer to the center, the speed increases dramatically. Near the inner regions of the disk, the gas can travel at tens of thousands of kilometers per second, faster than anything in the solar system. And as the gas moves, it rubs against itself. Particles collide. Magnetic fields twist through the plasma. Friction builds. All of this motion generates enormous heat. Temperatures inside the accretion disk climb to millions of degrees. At such extreme temperatures, the gas begins to glow intensely. X-rays, ultraviolet radiation, visible light. Energy pours from the disk in enormous quantities. In fact, the region around a feeding black hole can become brighter than the entire galaxy surrounding it. This kind of object is known as an active galactic nucleus. An OJ287 belongs to a special category of active galaxies called blazars. In a blazar, the black hole launches powerful jets of energy from its poles. These jets are narrow beams of particles moving close to the speed of light. They extend far beyond the galaxy itself, sometimes stretching for thousands or even millions of light years. In the case of OJ287, one of these jets happens to point roughly toward Earth. That means the light and radiation produced near the black hole travel almost directly toward us. This alignment makes the galaxy appear extremely bright, even across billions of light years. But the accretion disk surrounding the black hole plays another crucial role, because this disk is what the smaller black hole crashes through during its orbit. To understand the scale of this event, imagine the disk as a vast glowing ocean, an ocean made of plasma, millions of degrees hot, spinning at incredible speeds. Now imagine a black hole, 150 million times heavier than the Sun, plunging straight through that ocean. The impact is extraordinary. As the smaller black hole enters the disk, it tears through the gas like a cosmic bullet. Material is violently pushed aside. Shock waves spread through the plasma. The disk ripples outward from the collision point, but something else happens as well. The tremendous heat and pressure of the impact cause gas to expand rapidly. A huge bubble of hot plasma forms around the collision site. This bubble begins to rise above the surface of the disk. As it expands, it becomes visible to telescopes across the universe. This expanding bubble is what produces the bright flare observed from Earth. But the flare does not appear instantly. After the collision, the hot gas needs time to expand and cool. As it grows larger, it becomes visible from great distances. Eventually, the expanding bubble releases a powerful burst of radiation, a flash of light traveling across 5 billion light years. From Earth, astronomers see the galaxy suddenly brighten, then slowly fade again as the bubble disperses. But the process does not end there, because the smaller black hole continues its orbit. It plunges completely through the disk, emerging on the other side. Months later, the orbit carries it back through the disk again. A second impact occurs. Another bubble of hot plasma expands. Another flare appears. 2 flashes during each 12-year orbit, both connected to the same violent encounter between the black hole and the disk. These repeated impacts have shaped the structure of the disk itself. Over millions of years, the smaller black hole has punched through the disk again and again. Each impact disturbs the flow of gas, creates turbulence, redistributes energy. The disk must constantly repair itself as fresh gas spirals inward from the surrounding galaxy. But the disk is not only shaped by collisions. Magnetic forces also play an important role. Inside the disk, magnetic fields twist and coil through the plasma. As gas moves inward, these fields can snap and reconnect, releasing enormous bursts of energy. This process accelerates particles to incredible speeds. Some of these particles escape the disk entirely. They are launched into space as part of the powerful jets emerging from the poles of the black hole. These jets carry energy far beyond the galaxy, influencing the surrounding environment across vast distances. In some galaxies, jets from supermassive black holes can heat enormous clouds of gas between galaxies, preventing new stars from forming. In this way, black holes can influence the evolution of entire galaxies. The disk around OJ287 therefore serves many roles. It feeds the central black hole. It produces enormous radiation. It launches jets of energy. And it creates the brilliant flares that reveal the motion of the smaller black hole. Without the disk, the binary system might remain invisible. Two black holes orbiting silently in the dark. But the disk turns the system into a beacon, a distant lighthouse shining across billions of light years. Each flare tells a story, a moment when the smaller black hole tears through the glowing sea of plasma, a moment when gravity and motion combine to produce one of the most spectacular events in the universe. And every 12 years, as the orbit repeats, the disk of fire lights up once again, a flash from the depths of space, a reminder that even in the darkest regions of the universe, light can still emerge from the most violent encounters imaginable. The flashes from OJ287 begin their journey long before they are seen, long before human civilizations existed, long before the Earth looked the way it does today. Because the galaxy that contains OJ287 lies almost 5 billion light-years away. When one of its flares erupts, the light does not arrive immediately. It travels across unimaginable distances, through the empty darkness between galaxies, across cosmic voids, past clusters of stars that will never notice its passage. For 5 billion years, that light moves through the universe. Only then does it reach our telescopes. This means that when astronomers observe OJ287, they are not seeing it as it is today. They are seeing it as it was 5 billion years in the past. At that time, Earth was a very different world. Life existed only in simple forms. Multicellular organisms were just beginning to appear in the oceans. Dinosaurs would not exist for billions of years. Human beings were unimaginably far in the future. Yet even then, the two black holes in OJ287 were already dancing, already orbiting, already producing their repeating flashes, and those flashes were already traveling toward us, waiting billions of years to arrive. The first hints of this distant system appeared in the late 19th century. Astronomers studying photographic plates noticed that a faint object in the sky occasionally brightened. At first, the changes seemed random. The galaxy would appear dim, then suddenly brighter, then dim again. In 1891, the German astronomer Hermann Karl Vogel recorded some of the earliest observations of the object, but it would take decades before scientists realized something unusual was happening. Over time, astronomers began compiling measurements of the galaxy's brightness. By examining old photographic plates stored in observatories around the world, they could reconstruct its history. And slowly, a pattern began to appear. The flares were not random. They repeated, roughly every 12 years. That discovery immediately captured the attention of astrophysicists, because very few cosmic phenomena repeat so precisely. Supernova explosions occur only once. Gamma-ray bursts appear suddenly and vanish. Even many active galaxies behave unpredictably. But OJ287 showed a rhythm, a cosmic clock hidden in the depths of space. As telescopes improved, astronomers began studying the object more carefully. Radio telescopes detected powerful emissions from the galaxy. X-ray observatories revealed energetic activity near its center, and optical telescopes recorded the dramatic brightening events. By the late 20th century, scientists realized that OJ287 was not just an ordinary galaxy. It was a blazar, a galaxy powered by a supermassive black hole whose jet points toward Earth. Blazars are among the brightest objects in the universe. Their jets accelerate particles to nearly the speed of light. Radiation from these jets can outshine the entire galaxy surrounding them. But the repeating flares still required an explanation. Why did the galaxy brighten every 12 years? The answer finally emerged when astronomers proposed a remarkable idea. OJ287 might contain two black holes. Instead of a single supermassive black hole, the galaxy could host a binary system, two gravitational giants orbiting each other. In this model, the smaller black hole periodically crashes through the accretion disk surrounding the larger one. Each impact produces a flare. Two impacts during every orbit, two flashes of light, and an orbital cycle lasting about 12 years. The theory was bold, but it made a clear prediction. If the model was correct, astronomers should be able to predict future flares. And those predictions could be tested. In the early 1990s, scientists calculated when the next flare should occur. Telescopes around the world prepared to observe it, and in 1994, the flare appeared almost exactly on schedule. The prediction had worked. The binary black hole model gained strong support, but the real test came later. Because the orbit of the smaller black hole is affected by relativity, its path slowly rotates. This means the timing of future flares must be calculated using Einstein's theory of general relativity. If the calculations were wrong, the flares would appear at unexpected times. But the predictions continued to succeed. In 2005, astronomers predicted another flare. Telescopes watched, and once again, the galaxy brightened right on time. The same happened in 2007. Then again, in 2015, each successful prediction strengthened the model. OJ287 had become one of the most convincing examples of a binary supermassive black hole system. But observing such a distant object is never simple. The galaxy is faint. Its light must travel billions of light years to reach Earth. Atmospheric turbulence can distort telescope images. Clouds can interrupt observations. Even the rotation of the Earth limits how long telescopes can watch the object during a single night. To overcome these challenges, astronomers rely on global networks of telescopes. When the predicted flare approaches, observatories across the world coordinate their observations. As the Earth rotates, one telescope hands the observation to another, from Europe to Asia to North America to South America. Together, they follow the galaxy continuously. Space telescopes also contribute. Observatories like SWIFT, XMM Newton, and other space-based instruments observe the galaxy without atmospheric interference. They detect X-rays and other high-energy radiation produced near the black hole. By combining these observations, astronomers build a detailed picture of the system. They measure how quickly the brightness rises, how long the flare lasts, how the light changes color over time. Each detail helps refine the models describing the black hole orbit, but observing OJ287 requires patience. The flares occur only once every 12 years. An astronomer may witness only a handful of events during an entire career. Yet each flare provides valuable information. Each flash is another data point in the long story of the binary system, another confirmation that two black holes are orbiting deep inside that distant galaxy. And each observation reminds us of something remarkable. The light reaching our telescopes today began its journey 5 billion years ago. It left the galaxy long before our solar system looked the way it does now, long before mammals dominated the Earth, long before humans existed. Yet across those immense stretches of time and space, the signal survived, a faint flicker of light, traveling through the expanding universe, until one night, a telescope points toward a distant galaxy, and that ancient light finally arrives. A brief flash in our instruments, but a message from deep time. A signal from a cosmic dance between two black holes, still unfolding in a galaxy 5 billion light years away. In the vast darkness of the universe, most black holes remain hidden. They do not shine, they do not glow, and unless something falls into them, they are nearly impossible to detect. Yet systems like OJ287 reveal something extraordinary. They show that black holes are not always solitary objects drifting quietly through space. Sometimes they exist in pairs. Sometimes they orbit each other. And sometimes those pairs become some of the most powerful engines in the universe. The discovery of OJ287 changed how astronomers think about the evolution of galaxies. For a long time, scientists believed that most galaxies contained a single supermassive black hole at their centers. But the universe is not static. Galaxies move, they collide. And when galaxies merge, their central black holes are drawn together by gravity. The result is a binary black hole system. At first, the black holes remain far apart, separated by thousands of light years, but slowly, their orbit tightens. Interactions with stars and gas drain energy from the system. The black holes spiral closer together. Eventually, they form a compact binary, two enormous gravitational objects locked in orbit around one another. This process may be extremely common. The universe contains hundreds of billions of galaxies, and galaxy collisions occur frequently over cosmic time. This means binary supermassive black holes may exist in many galaxies across the universe, yet detecting them is incredibly difficult. Because most of these systems do not produce visible signals, their orbits may last millions of years without creating dramatic events. That is what makes OJ287 so valuable. The smaller black hole in this system crashes through the accretion disk of the larger one. Each impact produces a bright flare, and those flares allow astronomers to trace the motion of the orbit. Without that disk, the system might remain invisible. Two black holes orbiting in darkness, but thanks to those flashes of light, we can study one of the most extreme binary systems ever discovered, and what we learn from it applies to the entire universe, because OJ287 helps answer some of the most important questions in astrophysics. How do supermassive black holes grow? How do galaxies evolve? And how does gravity behave in the most extreme environments imaginable? One of the most important lessons from OJ287 involves the growth of black holes. Supermassive black holes do not begin their lives enormous. They start small, perhaps as the remnants of massive stars, collapsing into black holes only a few times heavier than the Sun. Over time, they grow. Gas falls into them. Stars are swallowed. Entire clouds of matter spiral inward through accretion disks. But mergers may also play a crucial role. When galaxies collide, their central black holes eventually merge as well. Each merger produces a larger black hole. Over billions of years, repeated mergers can build the gigantic black holes found in the centers of galaxies today. The enormous black hole in OJ287, weighing 18 billion solar masses, may have grown through exactly this process. Its galaxy likely merged with others many times during cosmic history, each merger bringing another black hole into the system, each collision adding mass, until the giant we observe today finally emerged. OJ287 therefore provides a glimpse into how the largest black holes in the universe may have formed. But the system also helps scientists understand the behavior of active galaxies. Many galaxies contain central black holes that are actively feeding. These black holes produce bright accretion disks and powerful jets. They release enormous amounts of energy into space. Such galaxies are known as active galactic nuclei, or AGN. Blazars like OJ287 represent one of the most extreme forms of AGN because their jets point directly toward Earth. When this happens, the radiation from the jet becomes dramatically amplified. The galaxy appears brighter than it otherwise would. This alignment allows astronomers to study the physics of black holes and jets in extraordinary detail. But OJ287 also reveals something else about the universe. It shows that even the most powerful cosmic events can follow predictable patterns. For centuries, astronomers believed that many energetic events in space were chaotic, unpredictable, random bursts of energy appearing without warning. Yet the flares of OJ287 follow a schedule determined by gravity, a repeating cycle governed by the motion of two black holes. And that cycle can be predicted using the laws of physics. This predictability transforms OJ287 into something rare, a cosmic experiment, a place where scientists can test theories of gravity and black hole behavior under extreme conditions. But perhaps the most profound lesson from OJ287 is about scale. The system lies 5 billion light-years away. The black holes involved weigh billions of times more than the Sun. The orbit lasts 12 years. The evolution of the system spans millions of years, and yet we can observe it. We can measure its flares. We can calculate the motion of its orbit. Human instruments built on a small rocky planet can detect signals from the depths of the universe. That ability is one of the most remarkable achievements of modern science. It means that even events unfolding across billions of light years can become part of our understanding of the cosmos. The flashes of OJ287 may appear distant and mysterious, but they carry information about gravity, about black holes, about the history of galaxies, and about the structure of spacetime itself. Each flare is a message from deep time, a signal traveling across the expanding universe, and every time we observe one, we learn something new about the hidden forces shaping the cosmos. In a distant galaxy, two black holes continue their ancient dance, orbiting, colliding with the glowing disk of gas, producing flashes of light that travel across billions of years. And here on Earth, we watch, quietly, patiently, waiting for the next signal from the depths of space. Far beyond the stars of our own galaxy, in a region of space so distant that its light began traveling toward us billions of years ago, two black holes continue their silent motion. They orbit each other slowly, patiently, locked together by gravity. One of them is a giant, a supermassive black hole, containing nearly 18 billion times the mass of the Sun. The other, smaller but still immense, contains 150 million solar masses. Together, they form one of the most extraordinary systems ever discovered in the universe, the system we call OJ287. For more than a century, astronomers have watched its strange flashes of light, a distant galaxy brightening suddenly, then fading again. At first, the flashes seemed mysterious, but over time, the pattern revealed itself. Roughly every 12 years, the galaxy erupts with a flare, not randomly, not unpredictably, but according to the motion of two black holes locked in orbit. Each time the smaller black hole plunges through the glowing accretion disk of the larger one, a violent collision occurs. Gas is thrown aside, shock waves ripple through the disk, and a huge bubble of hot plasma expands outward. That expanding bubble produces the flare that travels across the universe, a signal visible even after 5 billion years of travel through space. But the flashes of OJ287 are more than just distant fireworks. They reveal something profound about the universe itself, because this system allows scientists to study gravity under conditions impossible to recreate anywhere else. Near a supermassive black hole, space-time becomes deeply curved. Einstein's theory of general relativity predicts that objects moving in such extreme gravity will follow unusual paths. Their orbits shift, their motion slows time, their energy radiates away as gravitational waves, and in the case of OJ287, all of these effects can be observed. The orbit of the smaller black hole slowly rotates with every cycle. The timing of the flares changes slightly as space-time bends around the giant. Energy escapes through gravitational waves, slowly tightening the orbit. Each observation confirms the predictions of Einstein's theory with extraordinary precision. More than a century after general relativity was first proposed, systems like OJ287 continue to test its limits. But this distant galaxy also reminds us of something even more important. The universe is dynamic. Galaxies collide, black holes merge, gravity reshapes the structure of space itself. The cosmos is not a quiet place. It is filled with motion and transformation unfolding across immense spans of time. The binary system in OJ287 likely formed when two galaxies merged billions of years ago. Their stars mixed together, their gas clouds collided, and their central black holes slowly drifted toward one another. Eventually, they formed the binary system we observe today. Over millions of years, the orbit of these black holes has continued to evolve. Gravitational waves carry energy away from the system. The orbit shrinks, the black holes move closer together. Someday, far in the future, their dance will end. The two black holes will spiral inward faster and faster. Their gravitational waves will grow stronger. And finally, they will collide. When that moment arrives, the universe itself will tremble. A burst of gravitational waves will spread across space-time, a signal traveling outward in every direction, perhaps detectable by distant civilizations, long after our own time. But that moment lies millions of years ahead. For now, the dance continues. The smaller black hole circles the giant again and again. Every 12 years, it crashes through the blazing disk of gas. Every 12 years, the galaxy flashes with light, and each flash begins a journey across the universe. A journey lasting billions of years. The flare we observe today may have begun its journey before Earth looked the way it does now, before the continents reached their current shapes, before humans walked the planet. Yet across those immense distances, the light survives, traveling through cosmic darkness, until one night, a telescope turns toward a distant galaxy, and the ancient signal finally arrives. A brief flicker of brightness, a whisper from deep time. But that whisper carries the story of two black holes, locked together in an endless gravitational dance. A story written in the fabric of space-time itself, and somewhere, far beyond the reach of our instruments, the next flare may already be rising. Another bubble of glowing plasma expanding above the accretion disk. Another flash beginning its long journey across the universe. A signal from a distant galaxy, where two black holes continue their slow and silent orbit. The dance of OJ287 goes on, unseen, unheard, yet shaping space-time with every motion, and reminding us that even in the deepest darkness of the cosmos, gravity never sleeps.